like to invite the speakers for the next session to please come up to the podium, as well as the speakers from earlier this morning.
Okay, we wish to start our after coffee break session, and I wish to ask the chairman for three presenters. Dr. Katia Balal from Air Product, France. Technical economical assessment of sodium borohydride as a hydrogen carrier. Please.
Hello, I'm going to present you some technical economical assessment of sodium borohydride as an energy carrier for hydrogen. So, just to start, I would like to detail you some R&D air liquide approach for hydrogen storages. As you can see here on the pictures, there are many ways to store hydrogen for energy applications. Here you have the high-pressure composite tanks, which are composite tanks, and we also have to work on the connectics and integration of the tanks on systems. Here you have the intermetallic hydrate tanks, which can absorb hydrogen at low pressure. Here it is sodium borohydride, which the presentation is dedicated to. We have also the way to store hydrogen in a cryogenic form, in a cryogenic liquid tanks. And here there are many other ways to store hydrogen, as it was said during the previous presentations. Then we focused on the most promising technology to store hydrogen, and among them there is the sodium borohydride, which looks like a good carrier for hydrogen. And the objectives of the work was to assess the supply chain and the technology. It is more a system approach than a material approach that I'm going to detail in the presentation. So in the first step, I would like to give some technical assessment more on the storage performances. I won't detail the reactor design nor the reactor performances, but just the storage. For the economical assessment, I will give the example of the power telecom relay on remoted sites, and then I would conclude. So the first question was how to store hydrogen with sodium borohydride. The commercial products are powder, tablets, or liquid. The liquid form is a high sodium hydroxide concentrated liquid, and it is a very corrosive solutions. So that's the way to buy sodium borohydride today for fine chemicals. For hydrogen energy solutions, the solutions were low concentrated solutions for NaOH. These solutions are the typical millennium cell solutions. It is 20 weight% for sodium borohydride and 3 weight% for sodium hydroxide, and then it's water. The other solution is 35 weight% for NaBH4, 3% for NaOH, and the rest is water. The question is, are these solutions stable? Can we store them a long time for use of then for hydrogen? So we made some stability assessments in our laboratory. Here you have the test bench, which is a very simple one. We made the solution here, and or here, depending on the temperature, and we wait for the natural decomposition of the solution. The work plan was this one. We made many experiments at 50 degrees and with a low concentrated solution of NaBH4, around 20 weight%. And then we make the sodium hydroxide formulation vary from 1.5 to 6 weight%. We make the same experiment but with temperature. We perform experiment at 0 degrees up to 50 degrees. We make the concentration of NaBH4 vary too in order to see the effect from 7 weight% to 30 weight%. So these are the results. First, for the temperature effect, here you have the percentage of decomposition of NaBH4 as a function of time. So it's a 10-day, 20-day, 30-day, 40 days. And the blue curve here, you cannot see it very well, but it is the decomposition at 0 degrees, so the solution is very stable at very low temperature. Here it's the decomposition at 22 degrees. The solution was stirred or not stirred, but there is no effect of that. And as you can see, after 30 days, there are almost 10% of the NaBH4 which was decomposed. At 50 degrees, the decomposition was very enhanced, and after 30 days, almost 60% of NaBH4 was decomposed in the solutions. For the sodium hydroxide effect, we make it vary from 1.5% to 6%. Here it's always the same curve as this, and you can compare the curves. So it's 23 and 77 solution. And when the concentration of sodium hydroxide is higher, of course, the decomposition is lower. For the sodium borohydride concentration effect, so it's the same curve here, you can compare. The more there is sodium borohydroxide, the more the solution is stable. But there is also a decomposition. So the stability, we can define this slope. It is we can have a modeling of the initial decomposition of the curve. So it is this equation. If we compare the calculation of the slope and with the measurement, we have a good accuracy between the theoretical equation and the measurement. This is a special point which was out of the hypothesis of this equation. This is valuable for NaBH4 concentration lower than 40 weight%, for sodium hydroxide concentration up higher than 0.2 weight%, but lower than 10%. So, as we could predict it, NaBH4 solution decomposition increases with temperature, low concentrated NaOH solution, and low concentrated NaBH4 solution. We also performed some experiment on high concentrated solution of NaBH4. It is more a slurry studies, and I will detail it in another slide. So, after these laboratory experiments, we wanted to compare the storage of NaBH4 with other storages, which are the liquid hydrogen tank and also the high pressure tank. So as a function of, here you have a graph which gives hydrogen release as a function of time. This, you cannot see it, but it is the high pressure tank permeation, but it is very, very low, so it can be said it is nothing. The blue curves here is the composition of 35,3 formulation of NABH4. The thin line is when it is at 20 degree, and the large line, it is when it is at 50 degree, because when we have a system, the temperature can vary from low temperature to very high temperature, most of all when the storage is outside and during summer. So it is important to have this evolution of the decomposition of sodium borohydride. This is NaBH4 lower concentrated solution, and it is, of course, the decomposition is, of course, enhanced. We compare that to the boil-off of a cryogenic hydrogen liquid tank, and it is the black line here. So the conclusion is that the solution stability is comparable to hydrogen liquid tank boil-off. So the solution cannot be stable with time. So I compare this solution to I compare this solution with the fuel cell consumption, but the diagram is rather complicated to explain. But here you have the mass of hydrogen stored in the storage and the decomposition with time here. And in the blue line, it is on the right. You can have the mass of hydrogen which is released during the storage. But if you include the fuel cell consumption, of course, you can decrease the mass of hydrogen released during time. This is important as a safety point of view. So we perform also some assessment for the concentrated form of sodium borohydride in order to know if this formulation is stable with time, with a very slow concentration of sodium hydroxide. So we made many experiments, and we vary the sodium borohydride concentration and NaOH concentration as 40 degrees, and you can see here that the release is improved, but it's still existing. If we make the temperature vary, as it can be used in a reality, this, of course, the decomposition increase with temperature. So it is impossible today to completely avoid the hydrogen auto-generation in the storage. The conclusion is that depending on use, we have to make some compromises for hydrogen storage in the sodium borohydride. If we look at the weight performances, we need to increase the NaBH4 concentration. If we look at safety, we need to be careful of the amount of sodium hydroxide used in the solution, because it's a highly corrosive product. Moreover, always for the safety, we need to define an allowed loss of hydrogen in the storage. Most of all, there is a temperature, which is an important parameter to define, and we need to be careful to freezing. We did not watch at this parameter, but if we need to use it at very low temperature outside during winter, for example, we need to define the freezing of the solution. So the formulation will depend on that use. The same for high temperature, the ambient temperature. If it is very hot outside, there is an increase of the hydrogen generation. So the same for the storage lifetime. We need to define an allowed hydrogen loss during the storage, because we can, after 1 month or maybe 6 months, we can have no fuel anymore in the storage. Most of all, if we look at the handling of the fuel, we need to define if we want a liquid and a solid. and it is not the same for the reactor design then. And of course the fuel price, I will detail it in a few moments. All this study was not performed as for the reactor, so we don't have any information of the reactor design, and the formulation that we will define as a function of the storage use will have consequences on the reactor design, of course. For the economical assessment for telecom power relay and for remote sites, our objective was to have a roughly economical assessment in order to set bottlenecks. The hypothesis of the calculation is this. I don't know if it's very important that I detail everything. Just note that the sodium borate price was estimated as being 12 euro per kilogram. It is an air liquide estimation that we performed in our laboratory, but it is quite close to what we've seen in the literature and also in the Millennium Cell estimation. We made this economical assessment for two systems, 1 normal cubic meter per hour and 50 normal cubic meter per hour. So this is the result of the calculation. This are the uncertainty of the calculation. Just look at this one. We have the cost of the hydrogen produced by this system is around 6 euro per normal cubic meter, which is rather high. And as you can see here, most of the price is, of course, the price of the raw material. For the 50 normal cubic meter per hour system production, we have the same result. We have a price around 5.8 euro per normal cubic meter. And the most of the price comes from the raw material price. You have here the price of the system, the price of the transportation, the price of the tanks, etc. So the conclusion is that the raw material is an important bottleneck for the use of the technology, and there is a lot of work performed on the decrease of the cost of sodium borate. Today, 3.5 to 7.5 euro per normal cubic meter of hydrogen is just when we consider the raw material cost. Work is performed today to decrease this cost. In Air Liquide, we identify the bottleneck in the standard synthesis, and we are working on the new schemes today. For the logistics and the system, we will lead to a price of normal cubic meter of hydrogen for 0.5 to 1 euro per normal cubic meter for hydrogen, which could be interesting, of course. But as I mentioned before, in the first step of my presentation, there are some technical issues that need to be improved or to be bypassed, and I think that auto-generation of hydrogen for the storage tank is a bottleneck that is important. So now we focused on some technical items for the production and also for material handling and reactor design. I would like to thank people who work with me on that topic, who are Philippe Renaud for the experimental way, Serge Moreau for modeling, and the student Bertrand Orsal for the production assessment of the Schlesinger process, and also Valentina Mekina from the Heat and Mass Transfer Institute in Belarus, who worked on the stability of the storages. So I thank you for your attention and wait for your questions.
Thank you very much. Questions and a comment, please? Okay.
Could you comment on the, in terms of safety with this storage system, you're talking about the slow release of hydrogen. What about potential runaway of a given volume?
Sorry, I haven't understood your question.
Well,
Yeah,
can the system do some sort of runaway? I mean, if there's some sort of crash or
No. It's a soft decomposition. It's like bubbles, but very, very soft. It's not an explosion after all.
no, but is that decomposition exothermic or endothermic?
Yes. He's asking about it's an exothermic reaction, so he's asking about the potential for runaway decomposition. And I think the key is that the storage tank and the catalyst are not in the same place. And so it's only the material that's going through the catalyst bed that would be that issue. And the material itself, if it's not with the catalyst, has some stability.
I imagine that your sodium borohydride solution is not 100% pure. It probably has some trace contamination, which might act as a catalytic agent. So my question was, to what extent would the purity of the solution affect the self-decomposition?
It's a question we also asked to ourselves, but during the experiment here, it is a laboratory purity products, so it's very pure products. We thought about putting an additive in order to stabilize the solution, but we don't know what will be the consequences on the reactor and also on the purity of hydrogen that could be released from the reactor then.
Okay.
But if someone has an idea how to stabilize this solution, I think I would be interested in working on that.
Yeah, I just want to come back to the first question. I think there was a misunderstanding. What the colleague meant was that this is a potentially parametric sensitive reaction, which means it produces heat, the self-decomposition, and as we learned, was that the production of the decomposition rate is enhanced with higher temperatures. So the question was actually what happens if you store your tank outside in the heat in the summer. It becomes hot and produces heat and heats up itself, which means it could actually be that at a certain point the heat transfer rate from the tank to the environment is not anymore sufficient and the thing blows up.
It seemed you made a pretty big jump from heating up to blowing up, and that's
Okay.
So.
Yes, but in temperature the decomposition happens, but it is a slow decomposition, and as you could see on the curves, the more the decomposition is, the lower the speed is too. So when you decompose the NeBH4 in the solution, you also produce NeBO2, and your solution is more and more alkaline, basic, and then the decomposition is slower. So you don't have an increase of the decomposition as a function of time, even with the temperature.
I think also to add to that, you have, I think when you're talking about the tank, you're talking about an uncatalyzed reaction, and that will have some kinetic profile that you'll need to look at over the entire temperature range of interest. But then you also have the catalytic reaction that's in the
Yes.
catalyst bed.
But wasn't the study about the material without the catalyst?
Yes, it
Yeah,
was just the
okay.
storage of the
Yeah, right.
NeBH4 in the solution.
That was the question, because you get an increase of the reaction rate at higher temperatures, and at the same time you produce heat.
Okay, any questions? Okay, thank you very much. Now, next speaker is Tom Atlee, title is Novel Approaches for Onboard Chemical Hydrogen Storage with Focus on Ammonia Borane.
Very sensitive. That's the point. That's very sensitive.
Thanks. Good morning. It's a real pleasure to have this opportunity to share with you some recent results from our laboratory. I'm going to take a little bit of liberty and apologize up front. I have two abstracts in here. This showed up as an abstract for a poster and also as an abstract for a talk. So the poster abstract is what you have there, and I thought so you get your money's worth out of this, I'd talk about some unpublished stuff. The stuff that was in the poster was the ammonia borane work we've been doing on the scaffold material. This is some unpublished work from our group that's looking at the mechanistic side of things. So I'm going to instead of stepping away and taking a bird's eye view, I'm going to step down into it and try and get some fundamental questions answered about how hydrogen's released from this particular storage material. There's been a lot of talk also throughout the week about how this is an interdisciplinary approach to solving these problems. I think that goes all the way down to the fundamental level of studying these materials, and I'm very grateful to my colleagues. My background's physical organic chemistry, and my colleagues here involved material scientists, computational chemists, and chemical physicists that really helped to sort of get a good start of a picture of how hydrogen is activated or released from this particular storage material. It is sensitive. Okay. So ammonia borane is isoelectronic with ethane, and so but that's about where the similarities end. It stores a similar amount of hydrogen from a theoretical standpoint of about 19 weight%, so molecular weight's the same. But then you start looking at the other physical properties, and it's a completely different beast. The ammonia borane's a solid at room temperature. It melts at over 100 degrees. The ethane is a gas, of course, and you have to cool it quite a bit to make it a solid. And from a chemistry point of view, the bonding is quite interesting in the ammonia borane, in that the non-bonding electron pair donates into the empty p orbital of the boron to make it this dative bond, which is weaker than a covalent bond, but it's greater than conventional electrostatic hydrogen bonds and such. It has quite a substantial dipole moment, and the bond length's about 10% longer for that BN bond. And so that's sort of interesting in the starting material. We're interested in what happens to that bond length as we go to the product, and our computational Maciek is looking into the change in these properties. So a lot of hydrogen, 19 weight% for the material. The molecule has been was first synthesized back in 50 years ago, actually, in laboratories at the University of Michigan. And it wasn't until quite recently, just 6 years ago, that the structure of it was actually determined. And Crabtree and co-workers got a neutron diffraction spectra and showed what previously the borons and nitrogens had been switched around, and so that they thought this was a real anomalous molecule. But this was named, Crabtree called this, had a special characteristic in that the hydridic hydrogens attached to the boron act as a hydrogen acceptor. So it's sort of a non-classical dihydrogen bond with the protic hydrogens from the nitrogen. So from the get-go, you have some hydrogen that's already interacting with each other. And so the natural question is how does that affect how the hydrogen is released from this particular material? So we obviously weren't the first ones to think about looking at this. There's been some very, very elegant work that's come from Freiburg, from Gert Wolf and his colleagues that have been looking at this for probably around 5 years now as a potential hydrogen storage material. And the material is stable to air. It doesn't flame up. You can dissolve it in water. If you add acid, it starts to decompose. But neutral water, it's quite soluble and quite stable. So, and for transportation material potential, this has the MSDS of this is safe, and you can transport. You can even send it by airplane. I mean, if you look at the alanates or borohydrides, you have a hard time even shipping that across the country. So, So what the literature report said that there's two. And the nice thing is you can release this in a couple of different steps. So you can go through, heat this up, release 6 weight percent with one step, heat it up again, release another 6 weight percent. And then there's some reports that in the literature where you heat this up to over 900 degrees and you can release another equivalent of it. But we wanted to focus on accessible temperature ranges here, and so we looked at this in the scaffold material and hopefully had a chance to see some of the poster. The work came out just last month in Agnavante Chimie, looking at the kinetics and thermodynamic differences between the solid neat material and the stuff that's in the scaffold. But in this, this is our unpublished results, and we wanted to, once we started seeing these interesting differences in the scaffold material, we wanted to try and understand a little bit more about how the hydrogen is released from this material. So what's the mechanism? It's a solid state reaction. It melts 114 degrees, and it loses hydrogen quite rigorously at those temperatures. So, but you can release it from a solid state at temperatures as low as 70 degrees if you're patient, I guess. Or if you put it in a scaffold, things come off a lot faster. We wanted to get quantitative about this to know what the activation barrier is. So this is when we were doing some of our comparisons. And then, if we know something about the mechanism, the activation barrier, is there some catalysts that we can consider to try and improve the kinetics, or there's some other properties that can be used to enhance the rate for hydrogen release. And are there other products? There's reports that when you heat this up, borazine's formed, and borazine's isoelectronic with benzene and boils at around 50 degrees, so it's not something you want to have in your hydrogen stream if it's going to a fuel cell. So one of the first experiments to do is just to go ahead and kind of confirm what's been reported in the literature. Convince yourself that we're tuned up and ready to go. This is just looking at the volatile products in a temperature-programmed desorption, looking at the mass spec coming off. So you can see the hydrogen comes off in two steps that are sort of convoluted with one another. So this is just a ramped experiment. You can heat it up to temperatures below 100 degrees and just get the first equivalent off. And what's interesting is the borazine does come off with a second step. And so with hindsight, that's probably not too surprising. If you wanted just 6 weight percent for a material, then you could just completely avoid the borazine by not going to too high a temperature. And I think I have a pretty picture of the borazine here. But then if you want to get more hydrogen out of this, you got to be more creative, figure out ways to minimize the borazine formation if possible. So when you start digging through the literature to find out how hydrogen's released from this, there are probably about a half dozen papers, and 5 of those papers say it goes by intramolecular or unimolecular dissociation reaction, which is a bit surprising because when you first look at this and you have these hydridic and protic hydrogens that are interacting with each other, you might think it would go by a bimolecular or intermolecular pathway. But there were lots of experiments designed where they tried to trap the aminoborane, this double-bonded olefin species right here, and they were never able to trap it, so they said that it was very reactive, and so you couldn't trap the thing. But alternatively is you never make it because it goes by an alternative mechanism. And there is one paper that discusses back in the 60s about bimolecular pathways for hydrogen release. So this seemed like a pretty simple question that needed to be answered to get an idea of how the hydrogen is released from this, so we can start to think about how putting the hydrogen back in. So the simple experiment is to do some labeling experiments and look at the volatile gas materials that are coming off. So the litmus test experiment, I guess I'll call it, is to look for mixed isotopes of hydrogen coming off from this material in a solid state reaction. So what we did was we can make this, or you can buy this from Aldrich, and we can deuterate the material or make deuterated material. And so the concept is to make a homogeneous mixture, solid mixture of a per-proteated and a per-deuterated species. If it goes by a bimolecular reaction, we should see all these different isotopes, HD, H2, and D2, depending on how well it's mixed, kinetic isotope effects. We can, if it's a unimolecular reaction, we should never see the mixed isotope. It should just give you the polymeric species that comes off of there. So here's my cartoon slide. Here's a physical organic chemist's approach to synthesis. The ammonia borane itself could be synthesized quite easily. There's other ways to do it, but this, if we want to get the deuterium incorporation in here, the simplest way, you can bubble ammonia through a BH3 etherate solution, and then just excess ammonia, remove the solvent when you're done, and you have ammonia borane. A very clean, pure way of making it. And fortunately, you can buy deuterated boron THF and do the same process and get deuterium on your boron. You can put the deuterium on the nitrogen just by, it's very labile. You can exchange it with D2O washes, do that a few times and wash all the hydrogen out. And then the last one that we really want is for deuterated is just to start with the deuterated THF and then exchange that. So we have all 4 of these samples here now so that we can go through and see what the reactivity of these things are. So we need these for fingerprints for control experiments, but we're going to make an intimate mixture again of the ammonia borane and the per deuterated species. So one of the things, the controls that we were concerned about is that there's a report that ammonia borane, it's exchangeable. So if you throw in other amines with this, you can get exchange over a course of period of time that there was no kinetic studies done. So the one concern we had is that we wanted to make sure we had per deuterated, per proteated, and we did not have the mixed isomer of the species. And so the concept was to dissolve the ammonia borane proteated in one beaker, the per deuterated in another beaker, mix them together and rapidly remove the solvent, and then have a near homogeneous solution. But if there's exchange going on in there, that's going to ruin the experiment, because now we'll have, if we get HD, it could be coming from the isomer generated in situ in the exchange. So we talked to our Raman spectroscopist, and so she was able to look at the solids of all these materials. And since nitrogen and boron are relatively light elements to begin with, if you put deuterium on there, you can significantly stretch the BD stretch. And so you can look at the Raman spectra of this and get a fingerprint of each one of these species. And so the idea is then to kind of focus in on this BN stretch area, and you can see both the B10 and B11 isomer, as you'd expect. And when we focus in on that, we're very fortunate we do not make the mixed isomers. So we have, this is a solid state sample that we've prepared now, and we can go do this experiment to answer this just fundamental question about the mechanism. Are we going to see HD or not see HD? So go back, we're going to do the temperature programmed desorption this time, look at the mass spec, and we're not going to ramp it all the way to 200. We just want to look at the reaction in the solid state. We don't want to melt this stuff and have it exchange. So we heat this up. This was, I think, to 80 degrees, and lo and behold, we do get a substantial amount of the mixed isomer species. So we think this is pretty good, strong evidence that it goes by a bimolecular pathway. So you form hydrogen from the hydridic and protic hydrogens that are in close proximity to each other. Whether the reaction is concerted or stepwise, that still needs to be determined, and we want to get more detail into kinetic isotope effects and then also some Arrhenius treatment of the data. So you can start to draw some sort of back-the-envelope scheme of this thing where it undergoes some sort of dehydropolymerization reaction, and you just keep building this stuff up, and it releases hydrogen with each subsequent step. So what is the mechanism for this polymerization, and what's the activation barrier? And so you go back to the isothermal DSC experiments or with the mass spec, and so what you see is you can take this solid, and we're just going to heat it up to various temperatures, heat it up to 70 degrees, 75, 80, 85. It's an activated process. Add higher temperature, the stuff comes off faster. So can we do some sort of a simple treatment on this to get an activation barrier for this material? And when I first proposed this in front of an internal departmental seminar at the lab, the chemical physics guys showed up, and I said, well, this what we want to do is we want to get some sort of estimate of the activation barrier. We're going to assume that half the reaction's over when half the heat's released or half the hydrogen's released, and we have a half-life as a function of temperature and time, and then we can plot Arrhenius and get an activation barrier. And they said, well, that's a little naive. when you have something that looks, this is a sigmoidal kinetics. It's not a simple first or second order process like you see in solution. In sigmoidal kinetics, tell you that from people who are studying crystallization, there's 2 steps to this. There's some sort of nucleation that happens to start the reaction, and then once that happens, it takes off and releases the hydrogen until about half of it's gone, and then it can't overlap anymore. So this rate increases with temperature. It's got this sigmoidal behavior, so that it's indicative of some sort of nucleation and growth process for formation of hydrogen. In the thermodynamics, just to make sure we're on the same page, it's 21 kilojoules exothermic, 5 kcals. That's just what the Freiberg group measures. So this was a nice graph that the chemical physics guys gave me. The box is sort of a chunk of solid ammonia borane. The nice graphic on the other side sort of shows the hydrogen bonding dynamic. And so the question is, do you get some sort of polymerization growth along this way or up this way? And so you can kind of get into some of the details about how this reaction might occur. And I think, so here's, whoops, I did that too fast. So you get this nucleation site that happens, and it starts to grow. And if you get a nucleation site somewhere else, they overlap. And once they start overlapping, that's when the reaction starts to go down. And so because you have these depleted areas of hydrogen. And they introduced me to the Avrami equation. And the Avrami equation for this crystal formation, for crystallization, it has both a rate constant in it for the reaction that you can do as a function of temperature, and this exponent here, n, which tells you something about the growth, whether it's 2-dimensional, 3-dimensional type of growth. So you can fit the kinetic data that we did by just integrating the amount of hydrogen comes off or heat and get some information about the rate and try and find out how this polymer is growing. So this is, I apologize for squeezing this all into one graph here. So there's 70 degrees, 75, 80, 85 degrees. The blue line is the integrated release of hydrogen. The black line is the experimental fit to the Avrami equation. The red line is the fitting the Avrami equation with n equals 2. And so we tried it with n equals 3, and it wasn't as good a fit. It's somewhere, the best fit is somewhere between n equals 2 and 3, so it may be more complicated than just a single linear growth that goes on. And so this is something that needs to be addressed and understood a little bit more. But now we have these rates as a function of temperature. We can get an activation barrier. You plot an Arrhenius, you get to do Arrhenius treatment of this data, and turns out that the barrier for release of hydrogen from this is about 28 kcals per mole. But this is, you have to remember, this is the sort of the rate limiting step here. This is the nucleation event, because what's important about this is that if you understand what this nucleation event is, that you don't need a catalyst anymore. If you can put if it's a chemical process, so if the first step is rate limiting to make the first BN bond, the rest will just take off from there. Or if it's some sort of physical event, some sort of disorder you get by heating this thing up, and then it starts to lose hydrogen. So if you know those sorts of things, then you can get an idea of how to enhance the kinetics with this here. So sort of the conclusion, just we put this summarized at best, I think, with a kind of an energy level diagram here. We've got an activation barrier of 28 kcals for kind of the rate limiting step for just the starting with pristine material. And the heat of reaction is 5 kcals per mole exothermic. So that's the other interesting thing about this compared with carbon systems, which are endothermic for release of hydrogen. This thing is exothermic with release of hydrogen. And so that's going to make it a lot harder to just pressurize to put the hydrogen back on. But some of the stuff we've done with the scaffold material that we've published and it was on the poster, the enthalpy actually changed to almost thermal neutral. And so we're pretty excited about, we know to kind of demonstrate for the first time that you could just pressurize this and see hydrogen go back on here. And we have a Sieverts apparatus coming from Carl next month, and we want to do the measurement at high enough pressure so we can kind of demonstrate this reversibility. It'll give us some more information about the enthalpy. So bimolecular reaction, not a unimolecular reaction. Kinetic growth, nucleation, and it's somewhere between this 2 and 3D growth. And so the critical question really is, what is this nucleation event? Because then if you have that, you can possibly enhance the kinetics. And so we can seed the reaction and get the hydrogen off at lower temperatures or faster rates at the same temperature. And so that sort of wraps it up. These are a lot of people at the lab that have contributed to this, either intellectually describing, exchange of information, as well as doing NMR analysis. We've been involved with all the stuff we've been doing, and we've been involved with this about 16 months now through internal funding. One of the things we're very excited about is we're part of the P&L is part of the big Chemical Hydrogen Storage Center, and we'll be working. We have 3 different tiers in that group, and so this BN chemistry is really sort of a focus on its own, and it involves Tom Baker and Dave Thorne down at Los Alamos, and Larry Snedden at University of Pennsylvania, and Mike Heineke at the University of Washington and we're going to focus really on regeneration of these materials with that sort of funding. So with that, thank you for your attention.
Okay, start questions and comment, please.
Yeah, I have a question because you showed one of your slides was embarrassing because there was a diborane coming off, and my concern is about the safety aspect of handling these aminoboranes really regarding the emission of diborane, which is very toxic gas, as you know.
Toxic, flammable, yeah. It wasn't on any of my slides. We have not. We see borazine, which is probably not something you want to drink or breathe, but it's diborane. We do not see diborane when this thing decomposes. I think it's pretty hard in the solid state. I mean, you have to break that data bond a couple of times and have a couple of diboranes come together. We don't see ammonia. We don't see diborane.
No, I'm referring to the slide where you're showing the synthesis with ammonia mixed.
Okay,
yes,
yeah,
and
right.
then there was diborane coming off. So
no, that was a cartoon. That's diborane going in. So that you can synthesize it from diborane. So there's 2 approaches. If you add excess ammonia to BH3 etherate, you make 100% ammonia borane. If you bubble diborane through liquid ammonia, you end up getting about a 50% yield of ammonia borane plus this diammoniate of diborane, which is a real interesting species in itself. And we think that might even be the nucleation event. So that was a synthetic benchtop way of preparing these labeled materials. But in solid, we don't make diborane.
You mentioned that the reaction is exothermic, and at the same time you increase the entropy in the system upon decomposition. Why do you expect that you get it reversible when you just enhance the pressure?
Good question. That's why I think the mechanism is sort of important to know. We're not just taking hydrogen and putting it into a solid, and you're paying the entropy penalty for taking it from the gas phase, out of the gas phase. If it's actually a bimolecular reaction, the entropy penalty may not be as big because now you're taking a polymer of some sort and you're going to break that in half. So you gain some entropy. It's not going to compensate for the hydrogen, but I think that it will start to tell us whether or not the entropy penalty is less. So for 5K cows, it's still too exothermic. If it's thermal neutral, near thermal neutral delta H, in which we see when we put this stuff in this mesoporous scaffold, I think there's a chance to pressurize and reverse it. So we've done some more deuterium labeling experiments where we've kind of got some preliminary evidence that suggests that it can go backwards.
Any questions? Okay, thank you very much. Okay, we move to the last one. Approaching DOE hydrogen storage long-term goals by Piero Paolo Procini. Thank you.
Okay, thank you. Hydrocarbon represent the only way to power automobile. At the moment, it's very difficult to imagine another way to power automobile. But the problem in the case of petrol shortage is very how we can move without gasoline. And gasoline is very important because it's very abundant and low-cost material, and also it has a high energy density, but the problem is the pollution, and I believe that the perspective of sharing another decade with pollution from exhausts from internal combustion engine is not acceptable. Hydrogen car is emerging an alternative way to power automobile. Roughly speaking, to run about 100 kilometers, we need about 1 kilogram of hydrogen. And to meet market request, about 5 kilogram of hydrogen should be stored in the car. And to meet the DOE technical target, we need high gravimetric capacity, has a high 9%, and high volumetric capacity, and also the storage system cost should be very low, and the system fill time should be as low as 2.5 minutes. To meet the DOE goals, ideal metal hydride should have low molecular weight and high hydrogen content in mole of hydrogen per mole of metal, high density, low reaction enthalpy, and low cost. Now I want to show you the case of lithium nitride. It was shown that lithium nitride can reversibly cycle about 5% of hydrogen at 285 degrees, and we found that doping lithium nitride with titanium 2 mole percent, it's possible to cycle about 10% of hydrogen per mole of per gram of lithium nitride. This is this graph shows the pressure as a function of hydrogen content for titanium doped material. The pressure in charge was about 30 bar, and the temperature was about 285 degrees, both in charge and discharge. So it could be a good material to meet 9% weight percent for the system. And the problem is that it has a very high enthalpy. The enthalpy of the reaction is very high, at about 35 kilojoule per gram of hydrogen. And the high value of the enthalpy has several consequences. The working temperature is relatively high. Part of hydrogen has to be burned to allow other hydrogen to dissolve, and the parasitic reaction can reduce the hydrogen content to about 70%, and so only about 7% of hydrogen can be stored in lithium nitride. And so it means that it could meet short-term DOE goals, but not long-term goals. Technological challenges are the fabrication of high-temperature tanks working at about 300 degree, able to exchange heat very quickly. And about 1 megawatt of heat should be disposed in 2.5 minutes for a fast refill. This is a picture showing a car refueling very fast and a heat exchanger in the back to remove the heat. Okay. Another way to meet DOE goals is the hydrolysis of hydrides. The reaction of some hydrides with water can represent an affordable method to produce hydrogen, especially if we are able to recycling the water from fuel cell. In such a case, the gravimetric energy density is very impressive. The hydride must be regenerated off board. Among others, lithium hydride and sodium borhydride has an energy weight percent higher than 20%, and it represents a simple hydride and a complex hydride. And we tried to use this hydride, the hydrolysis of this hydride, to produce hydrogen by following the pioneeristic work of Aiello and others, and using steam instead of water to produce hydrogen. We designed this simple reactor in which the hydride in which steam is produced in a steam generator arrive in contact with the hydride that is contained in the reactor. The hydrogen and the water vapor arrive to heat exchanger, where water is condensed and hydrogen measured by water displacement. This is a picture of the setup for hydrolysis. We checked the different temperature. Temperature of the reactor and the steam generator can be set independently. And with this, the result of the experiment is that sodium borhydride is very hygroscopic material, and when the vapor pressure, the water pressure is very high in the vapor phase, part of the water pass from the vapor to the solid phase and absorb on sodium borhydride and form a liquid phase. The liquid phase formed by a solution of water and sodium borhydride start to produce hydrogen, but the reaction is difficult to control due to the formation of foam that bring the solution outside the reactor. Also, the sodium hydroxide that is produced during the reaction stops the reaction itself, and so we encountered a lot of problems. In the case of lithium hydride, but also in the case of we obtain the problem that we had, that is the volume of the reaction products is larger than the volume of the parent lithium hydride. So in some case there is a reactor occlusion, and the reaction enthalpy is very high, and so we need to refrigerate the reactor. And other technological problem have to be solved. For example, the hydrogen is produced at a very high temperature, and it has to be cooled before to feed the fuel cell, and water has to be recycled, and heat has to be used to increase the water temperature to form steam. This is a complete schematic view of the reactor that we are imagining, in which it's possible to observe the heat and water management. So technological problem can be avoided, and the major problem is the cost. Lithium hydride, the cost of lithium hydride is lower than the cost of metal lithium. And sodium borhydride, 60% is related to the cost of sodium metal, and to reduce the cost, in the case of sodium borhydride, both sodium metal production as well as a new synthetic way should be found. Roughly speaking, not depending from the kind of hydride, the cost of hydride is about €100 per kilogram. We saw 50 euros per kilogram in the case of sodium borhydride. To store 5 kilograms of hydrogen in a car, we need at least 20, 25, 30 kilograms of hydride. So it means that we need about 1,000 or 2,000 euro for a full. This could be the situation of the people that has a car. So how to decrease the cost of the sodium borhydride? We saw two ways just this morning. The synthesis of sodium metal starting from molten sodium hydroxide that can reduce the cost of sodium. Or otherwise, we saw this morning the work of Professor Sudandash and Altri, Sodium borohydride can be regenerated from borax using magnesium or other less expensive compound like aluminum or at least carbon that it could be the ultimate way to obtain low-cost sodium borohydride. We are studying in this direction, but we are only preliminary results. I was very at the end of my talk, and the conclusion is that solid metal hydride can meet some requirements, but not all. And to move to hydrogen-based economy, some technological improvement has to be done. But at the same time, we need a new culture model to be developed. And I believe that at the moment, only revising our style of life, it is possible to contribute to a cleaner environment. Thank you very much for your attention.
Okay, comment, questions, please. You have enough time, right?
Yes, I have a lot of time for questions.
Okay. No? Somebody? No? Okay.
You had carbon down as the source of electrons. Did you say you were working on carbon as well?
Yes, we started to work, but we have not any results to show.
I should say thank you very much for all the speakers.
Yeah. I'd like to invite all the speakers to come up, and we'll start our panel discussion. So our panel has the good fortune of having lunch after it, so it will be a fixed time, we believe. So I think as a prelude to the panel discussion, maybe we can, I'll just review a little bit of what we've heard this morning and where some of the areas of overlap and potential collaboration might be. So we've heard a number of concepts have been advanced for chemical hydrogen storage. There are a number of materials that look like they can meet the hydrogen storage capacity targets. Of course, everyone, I think, appreciates that the entire system will be quite a bit lower density than the material itself. There's a potential, as we heard today, for a liquid or a solid infrastructure even, rather than a gas-based infrastructure for hydrogen storage using chemical systems. Some exothermic and some endothermic reactions are possible, and heat management and controlling those reactions will be important for both concepts. Regeneration will likely be off-board, although I guess on-board concepts can be envisioned, but the focus seems to be on off-board right now. Brings up some fairly interesting infrastructure issues for an off-board regeneration concept that would have to be looked at. There are some of those regeneration concepts that would involve hydrogen, but some of those regeneration concepts will likely not involve hydrogen as a gas, and so maybe those regenerations can be coupled all the way back to the energy source that would have been used to make hydrogen gas in the first place. Energy efficiency of that regeneration is going to be extremely important, as we've seen discussed in the talks this morning. Recyclability of those materials will also be important. We heard kind of three general areas: sodium borohydride hydrolysis, where catalysts and systems for hydrogen generation are important, as well as concepts for taking BO bonds and reconverting them back to BH bonds for regeneration. And one of the themes there was that we may need cheaper or more readily available reducing equivalents or cheaper electrons to do that reduction chemistry. We saw some ammonia borane concepts, where there are now several concepts that are in the posters and were in the talks on how one can get hydrogen to come off ammonia borane. And as Tom Autry pointed out in his talk, I think the next challenge there is going to be how we regenerate those dehydrogenated BN species and how far you actually go. And then we heard several concepts on some endothermic dehydrogenation systems using organic molecules, where some of the theoretical energy efficiencies might be very good for the regeneration. The key there is likely rates and catalysts for the dehydrogenation, whereas the rehydrogenation really falls into systems that the chemical process industry already knows how to handle pretty well. So there's a list of about 7 things that might be worthy of some potential collaboration discussion. These are chemical processes, so catalysis is going to be very important, homogeneous and heterogeneous processes and rates for those catalysts, and some catalyst discovery, particularly for probably non-precious metals to make those catalytic processes go. Coupling of the hydrogen storage system with the fuel cell, as we heard, will put some stringent requirements on the type and amount of impurities that can be tolerated, and what the heat balance, how much heat will need to be taken away or provided for those reactions, mechanisms and kinetics of those reactions. A lot of these systems are molecular and very amenable to theoretical calculations for calculating intermediates, and so that's probably something that can be brought to bear. With respect to onboard reactor concepts, there are likely some opportunities for reactor engineering, simple, robust systems where one needs to control the interaction of the material with the catalyst. There's some examples on the posters on current systems. And from off-board regeneration, probably the energy efficiency aspects, but also the infrastructure aspects. And so with that, I think we can open up the panel discussion. Are there any questions, comments?
From an energy efficiency point of view, it seems that one threshold that you may want to or try to come underneath is those metals that require electrolysis in order to start the regeneration, and perhaps those processes that could be done by other thermal methods, perhaps where the electrons are less costly. It's where do you think we are now and for the different processes?
Anybody want to take that question?
I guess I can give it a try. In our study for looking at various ways for sodium borohydride production, we did evaluate a number of thermal processes, and just to summarize the results, our study actually indicated that to generate the reduction reagents required by thermal process are actually also very energy-intensive steps, and in the end, it doesn't really come out ahead of the electrolysis processes. People mentioned a lot the sodium, magnesium, and aluminum as 3 metals that used as potential reducing agents, and all 3 of them you can find ways of making the metals both thermally and electrochemically, and if you compare the energy efficiency, all 3 of them come out with the electrochemical process being more efficient.
Additional comments, questions?
I have a comment. I'm a boron chemist, and I think the regeneration of the compound of borohydride are only commented for a long time by old method. We are always trying to do very hard method to change boron oxide to boron hydride. I think boron chemists have to look to other methods, especially a soft method, which has been developed for a lot of chemistry and not for us. And I asked my colleague from Japan, because there is the meeting of boron chemistry this year in Japan, to ask to their colleague what can be new in new chemistry of rehydrogenation or changing from oxide to hydride on boron chemistry. I think something could be done, and we are changing for very few and very few changing sodium for magnesium and so on. If the process are more efficient, that's right, but the end of the purpose is the same. So I think we have progress to do, but in a larger way of chemistry.
I guess I'll add to that just a little bit. There are a number of metals, obviously, you can choose as reducing agents, but in the end, it's limited by thermodynamics. The redox potentials have to match the reducing power of the reagent has to be enough to break the boron-oxygen bond and change the oxidation state. So that's what I want to add.
I think you can think of that two ways. One is once you make a boron-oxygen bond, as you said, what are some other concepts that might allow you to manipulate that boron-oxygen bond as opposed to a direct reduction? And that's certainly something that I know in the Center of Excellence that we have for the chemical hydrogen storage, that's one of the tasks that we've set out to do collaboratively with groups like Roman Haas and Millennium Cell and some of the other collaborators. The other question that it bears out, of course, is how to get hydrogen out of these very appealing, very hydrogen-rich boron systems, but never make a boron-oxygen bond and fall into a deep thermodynamic well in the first place. And that, of course, is the other challenge, and we're seeing some indications in some of the other systems like the ammonia boranes where we might have a different thermodynamic balance.
It seems that if you need high temperature and lots of electricity, I would guess this process, or some of these processes, might fit well with nuclear reactor electricity. If CO2 is the thing that we really want to avoid in the long run, I think even environmentalists such as myself will have to embrace nuclear reactors as part of the mix, at least in the U.S. Just a comment.
Well, I think staying on the technical end as opposed to chasing that dog right now, I think one of the opportunities, as we talked about maybe, is the possibility. We have to realize when we make hydrogen, when we transport hydrogen, there are energy efficiency issues there as well. And so some of the opportunities might be to back up to that energy source and not go through hydrogen in the first place. And so if you can do that, you have an opportunity to get some credits for energy efficiency on your regeneration process that wouldn't exist in other cases where you used hydrogen. So it's a balance, I think. Comment, Professor Su?
About application of electrochemical reaction or application of thermal decomposition or thermal synthesis. But our point is not located to the electrochemical or thermal reactions. Just we focused our attention on the very active surface, surface excitation against the molecular molecular hydrogen. This is very easy to be decomposed at the extreme surface of metal hydride. So it is a good chance to make use of decomposed. It is not the monoatomic hydrogen, but it is a so-called proteid. So we are going to make use of such kind of very active condition state of hydrogen for synthesizing some kind and like our sodium borohydride. We can save the energy, so-called about Andrea's question that I didn't answer about that through some reason. But anyway, energy level is very low because of its own self-containing energy excited condition is very, very important. So, and we have now undergoing a project of how to make use of the excited conditions of the hydrogen and also mineral hydride surface. So I don't think it's a mineral hydride the application is good for hydrogen storage. No, I think it's the catalyst and also the electrode with the good surface. So we have, I think, such kind of ideas. Okay.
Yes, when we started thinking about the Chemical Hydrogen Storage Center, we were really concerned about that issue and the regeneration, so we diversified our approach to that. And as Bill was mentioning, to try and one of our 3 tiers is to just avoid the BO bond formation by looking at these BN bond materials. And I wanted to take an opportunity to say that we're not the only ones doing this. Mark Bowden had a poster on some of the stuff where he was putting substituents on the ammonia borane, and I think we're real interested in that and how that changes the thermodynamics. The neat reaction itself is 5 kcals exothermic, and as one of the questioners pointed out, that's still too exothermic to just pressurize with hydrogen. We've gotten it up to 0, and we're trying to understand how that happens. When we put this stuff on a mesoporous scaffold, we have some ideas with that. But if you can have substituents that change and you can dial in that thermal chemistry, then you might have something that you could possibly regenerate on board, or in the best of circumstances, you don't have that. We look at it just a simple, it's 5 kcals exothermic versus the hydrolysis, which is 60 kcals exothermic. So if you're going to have to put energy into the system, it's a lot less energy intensive just from maybe that's an apples to oranges comparison, but it's at least you're not starting way down in that well there. So I think there are people that are starting to look more at these boron nitrogen compounds. And then also RTI, I think they have a group that's looking at synthesis of the ammonia borane in Russia. And I'm going to take the diborane out of my slide presentation because I think that leads to some confusion. I mean, that's not the way we'd recommend making it. It's just a synthetic procedure to get there. So, but I think that alternative ways to get the hydrogen off these borohydride-like species are attractive thing to look at. And the way we really got started in this was we have a very strong computational group, and the group I'm in is half theorist, half experimentalist. And the question was raised by my theoretical colleague Maciek Butowski. He said, well, why is everybody putting hydrogen only on the anion? Why don't they put it on the cation? And so he called me up and said, why don't people look at ammonium borohydride? And so that's how we sort of got started looking at this. And ammonium borohydride was made. It loses hydrogen. It's unstable at room temperature. And so that's isoelectronic with methane. That's 24 weight %. So there's the thing we like about that. There's 4 different steps you could envision looking at for these boron nitrogen compounds. And so that's sort of what we focused on with the Chemical Hydrogen Storage Center, and with emphasis on regeneration. We think that the first 2 steps we looked at, the hydrogen comes off pretty low temperatures. I mean, you can get it off. The first one you can get it off at 60 degrees with a scaffold material. And then I know Los Alamos is currently doing some stuff with catalysis that has it coming off at room temperature. But I think that's the alternative, is looking at other borohydrides that you don't do the hydrolysis.
I just wanted to mention one other issue with the hydrolysis type reactions, how sometimes it's assumed that the water would be available from the fuel cell. If that's not the case, then the additional water would have to be included in the system calculation for weight and volume and so forth. And of course, the amount of water available from the fuel cell can depend on many factors like the operating load, external conditions. And I wanted to call on some of our industry participants, maybe Tarek from Daimler Chrysler, if they can comment on that.
I guess at Daimler Chrysler a couple of years back, we built a minivan called the Natrium, which ran on sodium borohydride fuel, a 20% solution similar to what was presented today. Just to maybe add one note to what was asked before, the potential for a thermal runaway as a fuel is just sitting in the tank. I can say for sure that we didn't have any kind of problem of a potential thermal runaway. We had our tanks sitting in the vehicle, sitting outside in the parking lot for an entire day at times in very hot summer conditions, and we didn't have such a situation. I think there is enough excess water in the system to prevent, a thermal runaway. We did have obviously some hydrogen evolution, but we were able to deal with that fairly easily with a catalytic burner in the tank. So that wasn't a very big concern to us. The other thing we looked into quite extensively was the amount of potentially recycling some water from the fuel cell to try to improve our overall gravimetric density. One thing that you find in automotive fuel cells particularly is that the amount of water available to you is much less than you would theoretically think it is. On average, you get between 30 to 40% of the theoretical amount of water that you can condense on an automotive system, given that most condensers are operating at the low temperature coolant of around 50 degrees Celsius, so it really limits how much water you can condense. If you want to condense more water, it usually comes at a big penalty in terms of heat exchanger sizes and condensers, which should be assumed to be part of the weight of the storage system. So it's very difficult to retrieve significant amounts of water from a fuel cell.
If I may add to that just a little bit, I think there are two places really within the overall system where you can have opportunities for recovering water, and one is, as you mentioned, from the back end of fuel cell, and really you can only account for a small percentage of that water produced at the fuel cell. Another opportunity is really, it's immediately post a catalytic reactor. There's a lot of water of condensation that you can recover and use again. And in fact, for practical solution concentrations up to 35%, you can use that part of the water to incorporate in the recycle loop, and without having to recover any of the fuel cell water to improve your system efficiency and storage efficiency. So it's only when you push the fuel concentration above 35% or higher, then you need to start looking for other places to get water from.
If we could entertain a slightly different question along the lines of the point that Alan McDermott was making to Alan Cooper's talk about incorporating perhaps something that might be catalytic directly into the molecule, the generic molecule that might be hydrogenated. And it kind of ties up into this boron discussion as well, because in the DOE's Center of Excellence for Carbon-Based Materials, we're looking at boron incorporation into different kinds of graphitic and nanotubular materials. And some computational chemistry done by Shengbei Zhang shows that a boron species can act, localize a hole, and participate in this non-classical dihydrogen bond, much like the transition metals do, with an elongated hydrogen bond. Now, normally we think about that as being advantageous from a point of view of physisorption, but that elongated bond is it's a hydrogen, a dihydrogen, stabilized in like a transition state towards perhaps being able to hydrogenate the carbon around it. So I wonder if that's just a pie in the sky idea, or if there might be some possibilities there.
I guess I wanted to also kind of understand more what Professor McDermott was talking about is the metals. Is like a homogeneous reaction, or it's not like you want to have a metal for every organic compound in there, or is it?
Well, I was suggesting a boron substituted right into the carbon lattice, and that boron species acting perhaps a little bit differently than the nitrogen that Alan uses in the
Yeah, I think you have to be extremely sensitive to adding any weight to the molecule that's not productive weight. You're always striving towards 1 hydrogen per heavy atom in the molecule, if that heavy atom's carbon or nitrogen or what have you. So I think we're always going to be limited to having something that's truly catalytic and can be present in extremely small amounts on the molecule. But I appreciate what you're saying. If you could add a functionality that's relatively light, containing boron, then you'll dilute the hydrogen carrying capacity a little bit, but if it gives you a big boost in performance, it might be worth it in the long run.
If you could simply substitute the boron for the nitrogen in your compound, you'd get weight savings, and you'd have all the carbons there. I don't know if that molecule exists or some analog exists.
Yeah, that molecule exists. It just turns out that the thermodynamics go in the wrong direction in terms of heat of hydrogenation, so it actually hurts you from that perspective.
Yeah. See, I'm somewhat interested with the organic, carriers, liquid carriers. Well, according to what we worked before, we thought if a liquid can be catalyzed to be hydrogenated or dehydrogenated, directly in the liquid state, it would be very easy to use the present infrastructure. Just to carry the organic liquid there, if we pump just send the hydrogen to the fueling station, either work it there in the refueling station or on the vehicle. That would be a very simple way and a very quick way. As we experimented on the hydrogenation of benzene into a cyclohexane and vice versa. Well, it seems to us it can work quite well, but only the benzene is toxic. As they said, it's not good to be used. So today I say, well, it's very interesting to me to see that you use decalin, and also the decalin then transform into naphthalene oil. It seems to be quite similar to the reaction of ours, but I have still some doubts, some questions. One is you add also some solvents, as it's mentioned. Which kind of solvent is added? Would that solvent hinders or doesn't interrupt the catalytic reaction of the hydrogen storage alloys we added in or not? That's one. And the second is that naphthalene or decalin harmful to the health and can be used as a organic carrier for the hydrogen or not on the market. Thank you.
In my case of hydrogenation and dehydrogenation catalysis, no solvent are used. Just neat liquid of aromatic compounds, including naphthalene oil, or of course benzene, toluene, and other liquid aromatic compounds can be hydrogenated in neat state. It is necessary to heat up. For example, at 150 degrees Celsius is one example, but the catalysis can act to absorb hydrogen into aromatic organic compounds, and then we can have hydrogenated aromatic compounds such as decalin, cyclohexane, and so on. Now, dehydrogenation in liquid phase is also done without any solvent. I talked on the superheated liquid film state. It's just the neat liquid of decarin or methyl cyclohexane. For catalyst surface, the active site is required to split the carbon-hydrogen bond by giving, in interaction, by giving electron from the side of catalyst active site to the CH sigma star orbital, which is antibonding, and can dissociate that CH bond. So the combination of CH bond and the catalytic active site nature is quite important, so that in some case platinum and platinum rhenium composite or platinum tungsten composite or platinum iridium composite are very effective. But you can notice that these kind of combinations are already tested in petroleum industry. They use that kind of bimetallic catalyst in petroleum refining. You know, the platforming changes into reniforming process, which means that the catalysis, the composite effect between platinum and rhenium, is superior to platinum itself. And I could show that the nickel ruthenium combination was effective as platinum itself. This kind of catalysis is now still underway, so no good theoretical prediction is unestablished yet. So we have to try and try. But I believe that it is very much expectable to have good economical catalyst. Working substances, commodity chemicals, no problem in cost or handling. It's quite easy. And so I guess that kind of approach would show us the way of hydrogen society or hydrogen economy. It might be the same opinion with you.
Alan, would you like to add to that, please?
Well, I think that was well spoken. I think that Professor Saito was referring to is the need to have relatively inexpensive, simple aromatic systems. Environment, health, and safety issues have to be extremely important as far as toxicity, and you mentioned that before with the use of benzene, so that if in the future this was the preferred method of hydrogen delivery and hydrogen storage, that you would have billions of gallons of these liquids being used around the world. And so therefore they'd have to be very safe, and water miscibility, toxicity, things like that would have to be considered, certainly.
Yes. Alan, coming back to the catalysis, you can expect this question from me. Is any advantage? I see the disadvantages, not the advantages, of having an homogeneous catalyst instead of the palladium supporter thing that you use. In other words, I mean, it's only a fraction of a percent that you need, and something can be. There are so many extremely good organometallic compound that can do the dehydrogenation in a very effective way.
Well, as I mentioned earlier, there are a few homogeneous dehydrogenation catalysts that are known in the literature. They actually, while they have some impressive ability to dehydrogenate molecules such as cyclooctane that normally would be very difficult to dehydrogenate, they have relatively low rates. One advantage you could foresee with a homogeneous catalyst is that could be dissolved into the liquid. And so therefore, as you circulate this liquid throughout the delivery pathway and back to hydrogenation, that the catalyst actually remains embedded with the liquid. And so you could envision that as one way to do this. We've actually been very, very surprised to achieve the high selectivity that we've achieved with homogeneous catalysts. The general rule of thumb is that heterogeneous catalysts can be very non-selective. Homogeneous catalysts can often be much more selective. And so that was a bit of a surprise and a pleasant surprise for us.
Just one comment to that. I don't want to be seen as contradicting my own colleague, and I'm not. But you really don't want to have a catalyst associated with the liquid when it's in the infrastructure, and the reason for that is safety. The liquid alone, no matter what it is, at least the liquids that we've spoken of, will never spontaneously liberate hydrogen, even upon heating. They must have the catalyst. The inability to to give up hydrogen is an enormous safety factor which you do not want to lose. Okay, there's the division of the division of the backyard barbecue, and if you've got the liquid carrier, you throw it on the barbecue, and it will maybe catch fire, maybe smother the barbecue, but you certainly don't want it to boil off hydrogen in the way that you've seen in Alan's video, because that could be quite dangerous. So okay.
Yes, but aren't there scenarios where some of the catalyst is going through a flow-through bed? Some of the catalyst particles are going to ultimately be detached from the bed and left in the residual product, and as time goes and it's recycled many times, the catalyst is going to get in the recycled material.
But you would need, you need not only a few particles. You need well, if it's homogeneous, it's all there, right? But a few particles, isn't going to make, a few particles in the liquid is not going to make a catalytic dehydrogenation reactor, right? But a homogeneous system would.
And then you'd have to be very sensitive to temperature control then in the event that you had a homogeneous catalyst or a large amount of heterogeneous catalyst that you don't desire to have in the liquid, because then you could get spontaneous hydrogen generation.
Professor Montgomery.
I don't know whether it's quite appropriate as a relative newcomer to this fascinating field to just raise a rhetorical question, and that is that what we have heard during the last few days is some very beautiful inorganic chemistry and very interesting organic chemistry of great potential use in transporting energy in one form or another from one location to another. One of the points that seems to be very important, however, is what energy are we going to try to transport? If we eliminate carbon dioxide producing energy, then it appears from the discussions the main type of energy we are considering transporting is electrical energy. If we eliminate any carbon dioxide producing energy. This then raises, I think, an interesting point of the other alternative sources of energy which we may wish to use. A few minutes ago, comments were raised concerning the presence of boron defect sites. I think here we can learn quite a lot from the whole area of semiconductor physics and the interrelation with chemistry. For example, Honda in Tokyo 25 years or so ago, by using strontium, N-type strontium titanate, had some very interesting results on photo decomposition of water into hydrogen and oxygen. This ran into some problems because of the chemical degradation of the N-type strontium titanate. However, in the view of new types of materials available, this would seem to be a problem which might well be overcome. We have talked about obtaining electrical energy by wind power, tide power, and the like, or solar power. But I think at the same time that we discuss this extremely important question of transporting energy from one place to another in one form or another, we should at the same time bear in mind the alternate ways of producing energy of a technologically useful type, whether it is bioalcohol, whether it is biodiesel, whether it is photoelectrochemical decomposition of water, and the like. So again, since we're talking about hydrogen storage and transportation at this meeting, this is possibly an inappropriate subject to raise. However, I think it is a subject which is in the back of everyone's mind as we run out of energy in the world. If we exclude carbon dioxide producing sources of energy, we need to at the same time be considering sources of energy that we can turn to.
I think that sets a really good context for exactly what we're trying to accomplish. And I think the storage device probably couples to what the energy sources are, and that may have some impacts on what the storage looks like, as well as the storage device needs to couple to the utilization, which is the fuel cell. And I tend to think of a hydrogen storage device and a fuel cell as basically competing with a battery as another example, I think. Any comments from as we seek to close shortly?
Just a comment on that. The hydrogen storage is really driven by the need to store energy in a mobile system, right? That's the point. And it would be less interesting if we really had a way to store that much energy as electricity directly. But some people must have done the calculations. I believe, and hopefully someone can comment, we are far away from that. We are far away from being able to store enough electricity to drive the kind of vehicle that we use at the range of, several hundred miles, right? But since we're closing, and this is Italy, just made me think of an interesting parallel between what we've just said and, of all people, Guglielmo Marconi. It's kind of interesting. When I think it was the year 1900, something like that, he had done his first experiments on so-called radio at the time, and the Italian government did not want to support him, so he went to England with all his equipment. And when he went through customs, he boasted, and this is interesting, he boasted that he could supplant, with his radio, he could supplant the whole telegraphic structure of the then British Empire. In other words, that that all those wires all over the world that were emanating from London, basically controlling a big chunk of the then modern world, would now be displaced by radio. And the British customs people took so much fright that they actually confiscated all this equipment. But in the end, Marconi was wrong. Radio made it not to replace, an existing infrastructure, but radio rather made it for mobile systems. Okay, the Titanic, the history of this, the Titanic, and all the rest of it. And there's an interesting parallel there. The key is in finding things, for mobile systems. We really have no problem in energy infrastructure with electricity. That's fairly well developed, as was the telegraph at the time, by my analogy. But the problem is in our desire to be mobile, and that's where our challenges lie. And clearly, we don't seem to be able to do with electricity, and we have to do it cleanly. And so, hydrogen is or appears to be the choice, and that's all. That's what we will work for. Thank you.
I used to have comment from two scientists who has been engaging in lithium borohydride and also lithium boronitride, and materials are classified as onboard materials. From which reason is, of course, thermodynamically speaking, it's a back and forth reaction that you have. But our boron-containing materials like sodium borohydride, it's classified as an off-board material. So I used to ask you, Andrea, and also Professor Orimo, about your comment on the boron-containing hydrogen storage materials, please.
Sorry, Seichi, I didn't get your question. Can you please say it again?
Okay. Your material, the lithium borohydride, it's, you have been working on the material, and it is so-called onboard materials because of the reversible reactions. So from your point of view, how do you think, and do you have any comment on the off-board boron-containing hydrogen storage materials, I mean?
So you are asking about comparing our direct hydrogen desorption from borohydrides and your process, which is off-board regenerative.
Oh, yes.
Well, I think it would be nice if the borohydrides would allow to have non-board reversible storage. But I'm not yet convinced that complex hydrides will ever be on-board reversible, because also for alanates we need conditions which would require, or which requires high pressures and rather high temperatures, and therefore it's probably also for alanates better to regenerate them off-board. But I'm really not a specialist for mobile systems, and I mean, we should ask our car manufacturers what they think how a future fueling system for cars should look like. But from the materials point of view, I see both systems are very interesting. The big question for me is for the water reaction with borohydrides, if this is ever going to be reversible between the borax and the borohydride, or if you have to go in the regeneration over the elements, over the complete dissociation of the compound, and in this case it's I think it's energetically not worthwhile to do it, because about 75% of the energy would then be wasted.
Thank you very much.
Can I add just a comment to that? I think onboard reversibility, at least in my personal opinion, onboard reversibility in itself is not the end goal. In the end, it's how much it costs to use a kilogram of hydrogen, for example, in a fuel cell to propel yourself, or to allow you to communicate or to run your laptop for 12 hours without having to plug into a phone. I think, just maybe this is not a entirely politically correct comment, but I think in the end, to bring the fuel cell technology to commercialization, it will come down to the cost factor, the overall system cost.
Can I ask to Professor?
Okay. I'm interested in the, of course, BH system and also NH and also BNH system. All I'm interested in, and all system is so far so stable. That's why I agree with Professor Suda. It's still not on board system, but our research direction is destabilization of the complex hydride, including BNH systems. So that's why in the future I should like to have a destabilized system. In that case, maybe possible to use onboard reversible materials. And also one more comment on BNH system, just my comment. So I'm pretty sure the most stable phase is ammonia brine compound in the case of BNH system. But if I would add one more element, like for example lithium, we can prepare the completely different compound made from the BNH system. For example, as I explained in my talk, so sometimes we can prepare lithium BH4 and NH2 systems. It's not stable phase. It's not stable phase, but completely different to the brine ammonia system. Okay, so my challenge is to completely change the atomistic and also electronic structure, even in the metastable phase. But I try to try that. That's my comments.
Thank you very much. Thank you, both of you.
Okay, so this could bring us to a closure of this very interesting morning session. And before we all can cross the courtyard to lunch, Dr. Garibaldi has something.
I have some announcement to do. Lunch is ready. Before lunch, we would like to take a picture of all of us outside the church as a souvenir of this conference and a souvenir of Lucca. Please be back from lunch at 1:30 sharp, because we would like to conclude this conference at 2:45 before the departure of the bus to Pisa. It's a nonsense that one half of the people leave and the other stay here. So please enjoy the lunch, but be here at 1:30 sharp. Thank you.
Start. This is the last lap of the conference, and we aim to end by 2:45, so those that need to be at the airport can leave promptly in the 2:45 bus. So if you can all take your seats, we'd like to start by summarizing the panel discussions that were held after each technical session. Again, the purpose of this conference was really to focus on the technical issues, and then after each facilitator reports out a summary of the panel discussions, we'll have a wrap-up, and Mark Steen from the European Commission will provide a summary reminding people of the overall objectives of IPHE and the next steps, the process and so forth, of forming collaborations and eventually submitting proposals. So the first speaker is Rosario Cantelli, who will summarize the session on metal hydrides.
We were recommended to speak no longer than 5 minutes. Fortunately, we prepared the transparency figures, and I will briefly talk about reversible onboard storage, metal hydride research and development. Però non funziona sta cosa, eh? Okay. So, alanates. Pros and counters. Pros are dehydrating kinetics and cycling behavior. Promising, positive. Counters are capacity less than 5%. The quantitative results obtained up to now are for storage capacity from 3.5 to 5 weight percent at temperatures between 100 and 150 degrees centigrade with enthalpies of about 37 kilojoule per mole. The comment is sodium alanates are best and most studied. Other alanates should be explored. Amides. The pros is capacity and cycling behavior. Counters dehydrating kinetics. Quantitative results are promising from 5 to 9 weight percent. Temperatures are still a little bit high. We included between 170 and 250 degrees centigrade. Enthalpies 43 kilojoule per mole. Mixed metal amides show promise. Borohydrides. Pros are capacity, counters, kinetics, reversibility in some cases. Quantitative results good, 9% about in weight. Temperature rather high, 300 degrees centigrade. Enthalpies 45 kilojoule per mole. Mixing with binary hydride shows promise. Applications. We have heard about the high-pressure metal hydride tank that has been developed by Toyota. We also heard about optical hydrogenography that has been shown to have diagnostic applications for hydrogen storage. Highlights, adequate dehydrating and rehydrating kinetics have been achieved with sodium alanate. Mixed amides found to have high capacity, reversibility, and improved kinetics. Borohydride binary hydride mixtures found in some cases to be reversible. Mechanism of reversible dehydrating of doped complex hydride found to involve high mobility defect hydrogen complexes. Barrier discussed, reversibility, kinetics, thermal management, and others. Ongoing collaborations, University of Hawaii with the University of Rome La Sapienza, University of Milan, IEFE Norway, General Electric, University of Tohoku. National University of Singapore with Sandia National Laboratory, Institute of Applied Energy Japan, and Wolf Germany. Tohoku University with the University of Hawaii, Toyota, University of Fribourg, and Sandia National Laboratory. University of Fribourg with University of Tohoku, Amsterdam, IFE, University of Birmingham, University of Hiroshima, Toyota, and BMW. Then we have MPI with Opel, General Motors. Those are the ongoing collaborations. Proposed collaborations are University of Rome La Sapienza with the University of Hawaii, University of Milan, and AIST Tsukuba. University of Salford, University of Tohoku, University of Fribourg. That's all. Thank you.
So we'll continue, and then we'll take some questions at the end. So the next speaker is Gavin Walker, who will summarize the high surface area sorbents and carbon-based material session.
Okay then. From the carbon-based materials, high surface area absorbance and novel concepts session, then I'd like to thank Mike Heben and Rishad Shaheen for helping me in the task of reporting on what happened. So with the presentations that we had, then the main scientific and technical results that we feel were coming to the fore there were increased hydrogen storage densities through these metal-assisted systems. Also, it was nice to have the theoretical models as well, helping us to understand what might be happening in the adsorbents, as well as showing the way in which our experimental results and systems might develop. And that there was some theoretical modelling there predicting up to 9% in carbon-based systems, which gives us incentive to continue working in the area to try and realise those types of uptake values. But there's, of course, a need to understand the factors governing the energies of adsorption and how we might design those adsorbents so that we can get enthalpies of adsorption of around about the 6 kilocalorie per mole target that was being shown in many of the presentations. Overall, we had 6 oral presentations, 14 posters. So just to quickly go through the types of systems, there was nanotubes and nanofibers from the carbons, the MOFs, zeolites, inorganic nanotubes, and conducting polymers. I think the interesting thing there is that it's showing quite a wide range of different types of materials, trying to find solutions to the hydrogen storage question. But also, we had a presentation, and there were also some posters included, looking at trying to improve metal hydride kinetics, incorporating things like carbon nanotubes in. And I think an important factor is how are these carbon nanotubes actually affecting the kinetics, in what manner is it affecting the mechanism. There were also included some characterization papers, and I think something that most people in the carbon area will agree with, working on just the carbon side, is that they're not very well characterized. They're not particularly nice materials to characterize. So it's very important, the characterization side. And there's a range of technique-based posters or papers using things like neutron inelastic scattering, proton NMR, and looking at anelastic properties. And as mentioned before, the theoretical papers, they're also very important, helping us to understand the types of interactions that might be occurring with our materials, but also in developing new materials that will hopefully realise significant hydrogen uptakes. And examples there are hydrogen interactions with carbon nanotubes, exploring these Kubas-type complexes, and also looking at carbon-metal hydrogen complexes and how these might be stabilised. So in summarising the collaborations, this list is not going to incorporate all the collaborations for the people that are here at the conference. We went through the posters and the oral papers to try and distill a list of collaborations. So my apologies if there is a collaboration that you've got that's not on here, but I'm sure there'll be opportunities to add to this list, as I assume this information is going to be going up on the web somewhere. So examples include looking at these metal carbon nanotube multi-component systems. It's a collaboration between China and Australia. With the neutron inelastic scattering, then Keith Ross, as he said before, send him your samples. He'd love to do some experiments for you. But there was a particular example in collaboration with CNR in Italy using the ISIS facility in the UK. Also from my own work with the graphitic nanofibers, we're collaborating with Professor Fuji's group at the University of Hiroshima. And again, looking at the characterization of the materials, then dynamic gas adsorption in CNT's project that was between the University of Rome and Max Planck Institute in Germany. And the last one on the list here, metal-assisted CNTs, which is a collaboration that's been going for a number of years now between Richard Shaheen and Mike Heben. So the next couple of slides, we're trying to distill out some of the thoughts that came about from the panel discussion session, and the collaborative areas, potential for new collaborations. We thought it's very important to try and build up collaborations and communications from the theoretical side and the experimental side. So the first two, they might sound rather similar, but it's approaching it from two ends of the story. So combining theoretical models and experimental results for carbon-based systems, but also for other adsorbents. Quite important, looking at the experimental design to try and validate some of these new theoretical predictions. So there's some interesting work going on from the theoretical side. Can we actually produce that in a real system? There was also a feeling that we should try and build up more collaborations across the adsorbents and metal hydride communities, so we could try and collaborate and understand and develop new metal-assisted hydrogen interactions. We're going to, of course, get more innovative ideas if we do look at these cross-multidisciplinary activities. And also, as I said before, characterization of the especially with the carbon systems is crucial. So looking at new experimental techniques to help understand those materials. So some things that were brought up in the discussion session, then the role of carbon in metal-assisted carbon systems. It's a question that we've got to answer. Is the carbon there just acting as an unreactive support, or is there some synergy between the carbon and the metal? Potential for organic metals was raised as another area of that should be pursued. I don't believe there's been much work in that area yet. With the MOFs, then it'd be nice to see the work not focusing just on the surface area of the materials, but I think there's an awful lot of examples in the literature now, and was presented here as well, where they're trying to modify the chemistry of the MOFs to enhance hydrogen uptake. And an example of that is looking at, is it the oxide tetrahedron where the adsorption is occurring, or is it the organic linkers, and which is going to be the most productive of those two sites to actually target to increase the hydrogen interactions. And last slide, looking at new potential collaborations. This list of collaborations it's not an exclusive list, and it's, as you can see from the names of the participants down there, it was really developed by myself and my two co-chairs. So my apologies for the limited range of collaborations in it involving those three institutions, an awful lot. Again, we would like to invite any other groups that would either like to contribute to these themes or have other areas of collaboration to pass on that information to us. So some examples, continuing the single-walled nanotube system designs between NREL and HRI. There are a number of groups that are working on metal-assisted carbon-based materials, but the carbon substrates themselves are very different. So building up some collaborations across those different carbon systems could lead to some real breakthroughs in our understanding. So some groups there would be Nottingham, NREL, Oak Ridge, and a question mark to include any other groups that have interests in those areas. There's a collaboration being proposed by HRI, Max Planck and Caltech, looking at modified carbon-based systems. Also looking at thermal management issues in metal hydride systems, and can us in the carbon community help with that, looking at incorporating nanotubes into the metal hydride particles to improve the thermal management. On the characterization side, analytic spectroscopy from Cantelli, that's going to be a collaboration with NREL, or a proposed collaboration. And also, again, with a number of systems, people are interested in using boron and nitrogen to substitute into the lattice. So building up some communication between the groups working in those areas, especially across the theoretical and experimentalists. And thank you for listening.
Thanks, Kevin. And so now Gary Sandrock will summarize the discussions and activities in the stationary storage session.
Okay, I guess our session sort of covered everything other than vehicular storage. It hydrogen transport, off-board storage, and stationary application of many kinds. In fact, the world of hydride applications, and you can say the same about any other successful medium, is quite elaborate. We've covered only this vehicular area. There are stationary, portable, or thermal compression application, not only the compression of hydrogen, but closed thermodynamic systems. There are separation of isotopes, mixed gas, purification, gettering applications, batteries, and many of you know and own nickel metal hydride batteries, and a number of other odd applications. Several of these actually were covered, if you look closely, either in the posters or in the talks and places. But we're going to focus mostly on stationary and allude to some of these other stationary, portable, and allude to some of the other applications. In general, the feeling with stationary, I think, contributed mostly by our industrial partner Air Liquide, is that large-scale storage of hydrogen is not likely by a metal hydride, simply because the ratio of the high cost of the metal to the relatively to the hydrogen value here. Large-scale storage is going to be underground or underwater systems, or even in bladder-type systems or high-pressure systems. The oral presentations were three. We're the smallest session, and I maybe should be the shortest speaker then. All of these three speakers, France, Japan, Russian Federation, talked about what are sometimes called the metallic hydrides or intermetallic hydrides, those things that will work well near room temperature but have relatively low capacity, less than 2%. I've listed the poster presentations that are applicable to this particular topic. There were a few on the low temperature hydrides, these, and I've also listed the poster presentations on magnesium. Whether magnesium is a good stationary or portable storage system was somewhat debated in our session, as you remember here, relative to the problem of the high temperature enthalpy needed for the desorption here, but I'll get back to that in a minute. The status that sort of came out of the meeting is that there are many low-temperature hydrides available, the intermetallic compounds, AB5, AB, AB2, the body-centered cubic solid solution alloys, nanocrystalline magnesium and alloys and composites. These alloys, except for magnesium, can easily be fine-tuned thermodynamically, but offer only about 2 weight percent. The general feeling that 2 weight percent will certainly fit in many smaller scale applications depending on the price of that 2 weight percent. Magnesium offers great weight percent, but not so easily tuned thermodynamically. That's the problem we discussed. And there are many secondary non-thermodynamic properties that are unknown and need to be developed. And the exact requirements for these many applications I've talked about are not always known. Now, we're going to need some interaction between those who are building and designing devices and those of us that are making material to fill them. So the important secondary properties that came out of our meeting were these: the cost of the material is sort of a primary consideration in medium to even small size application. That means the raw materials cost and the production cost. There's optimum manufacturing. There's debate on magnesium and nanomagnesium, which many of you are working on. Can you really, if you get fine enough, change the thermodynamics of magnesium? Some said yes, probably. Some said no, probably. Some said no, certainly, I suppose. You may know a couple of those. What seems to be largely missed in many of the, even the old-fashioned hydride, the safety, pyrophoricity, tank bulging, cyclic life is largely unknown, as Seiji said this morning. That's not only gases impurity problem, but disproportionation problems relative to the stability of the alloy or intermetallic itself. Thermal conductivity and heat management is a major problem. Maybe it's not our problem because it's basically a mechanical engineering problem, but we cannot escape it. And again, there was some debate on are there really thermodynamic advantages other than non-kinetic advantages to nano-sized materials. Ongoing collaborations, I haven't been very specific here, but there are a number of them within the IEA, HIA, as you saw me talk on Monday. There are a number of them, very nice ones within the EC, High Train, High Story, many others. There are a number of bilateral and regional R&D activities. I was at a NISTOR workshop in Iceland a couple of weeks ago. There are many around, and there are others that I probably don't even know about. As far as the new collaborations, I can't be specific as to the individuals involved in the collaboration, but I'm really just focusing on here the areas that seem to come out of our workshop and the talks themselves, and economic analyses of production techniques, especially for nano-sized powder, some interaction between the storage medium scientists and those who run big metallurgical plants or no metallurgy. System designs and duty cycle analyses. Some things like storage depend on how often the storage is used. 1 week is uneconomic. 5, 10, 20 minutes may be economic. So we need the cost and property requirements and the storage material that the storage material developer must use as targets, and we need to get those from the analysis people and the engineers designing things. And if you look at that slide I showed of the mini application, we need to know how the targets we must shoot for change with these many different non-vehicle applications. I think everybody, privately speaking and in the meeting, realizes that systematic safety studies are probably lacking, probably the most important. Maybe it should be the highest on the list here. And even with these relatively benign metallic hydrides of 5, 10, 20, 30 years ago, there are still unknowns relative to their use from a safety point of view. And again, finally, determination. Really look at this nano-sized area. There were several people who didn't feel nano-sized were going to get us there, and several people who did. Certainly nano-sized has gotten us on kinetics. What else can nano-sized materials give us? Thank you.
Thanks, Gary. And now we'll hear from Bill Toomis, who will talk on behalf of the chemical hydrogen storage session co-chairs.
I think the electronic ink is not dry on this one, so we'll...
Well, while we're waiting for that to load, why don't we, let me emphasize again that our objectives for this conference were really to just start the process of initiating collaborations, potential future proposals, joint projects, and really what we wanted to do was provide an overview of the current state of the art, recent technical progress in hydrogen storage. There are many experts here in the field as well as newcomers from around the world, and identify some of the key barriers, areas for potential collaboration, and then just start the networking process. So if we can open it up for one or two comments from the audience on other potential collaborations or potential projects. Let's do that now. Scott.
I'd like to propose that just as Richard has told us we need to look at excess absorption and physisorption, it might be nice to try and get some excess collaborations out of this meeting. A lot of the collaborations we've just seen probably would happen at any really top-flight technical meeting where international parties come together. But I'd like to propose that it would be nice if we had collaborations across the areas that are reporting out to us. And the way that I see to do this is to look at the various levers we use to keep hydrogen in a small space, be it pressure, temperature, or chemical bonding. Now, the folks at Toyota very nicely showed us what happens when you try and use two of those. And I would suggest that there's a lot of fertility for two areas to work together in a collaboration that might never have happened except for this meeting if you try and go across those boundaries that have no really good reason to exist other than we like to stay in our discipline. And to give two examples, though I don't mean to say they're the best examples, I think the folks here can probably think of better ones. But if we were to use, for example, the ammonium borohydride that Tom Autry talked about that's unstable at room temperature, and put that in a high-pressure tank, would it be stable? Could you reverse back and forth between the BH4 NH4 and BH3 NH3 with just hydrogen pressure at, say, 300 or 700 bar? If so, you'd have a much better material than what was shown to us already. And because it disproportionates at minus 20 C, it should work very, very nicely. One idea. The other one would be that, again, playing off of Tom Autry's poster this time, they've shown that you can change the properties, the thermodynamic properties of the borazane material in their mesoporous scaffolding, but they've only tried one or two different kinds of compounds. We all know that there's just a host of mesoporous materials and a bunch more that can be created with just a little effort. So could the BH3NH3 be put profitably in some other scaffolding, if you will, some other material like multi-walled carbon nanotubes or zeolites or what have you? Or could something else be put in the sort of scaffolding that PNNL has been using? These are the sorts of things I'm thinking about where you're using two of those levers together at a lower amount to try and establish the same kind of storage. Thanks.
Thanks very much, Scott. I think Scott brings up an excellent point in terms of how we tend to stay in our own areas. So thanks for helping us to think outside the box. I think many of us know that there are conferences that we go to that maybe are just specifically metal hydride or more focused on carbon or chemical. So this time we've seen all of them, and I do also encourage you to think across boundaries. Now let's go to Bill Toomas's presentation.
Okay, and I need to apologize to the speakers from this morning because the time allotted for us to put this together will not do justice to the fine talks that we heard this morning. But, eons of solar energy have been stored through biological and geological processes into a material that we use today, where the energy source is also the energy storage material. And so the challenge of chemical hydrogen storage is to capitalize on that same concept. You can store a lot of energy in covalent bonds, but how do you get that energy in there fast, and how do you get it back out in the form of hydrogen is really the challenge. And with chemical hydrogen storage, just an overview, liquid or solid fuel infrastructures may be possible. We saw some examples of that at the conference. A number of concepts have been demonstrated. One of the appealing things is the material hydrogen storage density of these materials look like they'll do fine for the targets that have been put out. Of course, the entire system and what reactor and everything else is going to be needed has to be included as we move forward. And we've seen examples of exothermic and endothermic reactions, all of which have been catalyzed to generate hydrogen. And this is an area not unlike the other areas where regeneration is key. One could envision onboard concepts, but it certainly seems at the moment that off-board regeneration is likely. Energy efficiency is going to be important, not just what the maximum theoretical efficiency is, but what the actual efficiency is as you start to couple. recyclability of these materials as they're cycled through the hydrogen on, hydrogen off processes. Some of these processes, based on the thermodynamics, are going to be able to take hydrogen directly and store them. Others are actually going to have other reaction pathways that use energy sources to put hydrogen on, and then H2 would come off. And so we saw three general concepts presented in the posters and the talks at this conference: sodium borohydride hydrolysis, other boron compounds that did not use hydrolysis, and the examples presented were ammonia borane, and some nice talks and posters on dehydrogenation of organics, both carbocyclic systems and also heteroatom substituted systems. And I wanted to point out that there was one poster that looked at ammonia and putting ammonia on coordination complexes as a way of moving ammonia around. So I'd like to go over these three areas and some of the general summary of what we learned from this conference, what some of the key barriers are. For exothermic, sodium borohydride hydrolysis is exothermic. There are catalysts out there that have been looked at. There are systems that are out there. We heard some hydrogen generation systems from Professor Suda, from Ying Wu from Millennium Cell, and there were several examples in the posters. Erlikid talked about the stability of those solutions, and we also saw a very nice poster from Daimler Chrysler about the Natrium car and some of the positive attributes of that and some of the work that still has to be done to deal with some of the systems engineering and materials compatibility. I don't think I'd surprise anyone in the audience that regeneration is really the linchpin for this system, taking a very stable BO bond and getting it back to a BH bond. It's all about energy efficiency. We saw some economic analyses and some cost estimates, both from Italy and from Erlikid. It seemed that certainly the main cost element there was the sodium metal. And certainly we saw some talks from Ying Wu at Millennium Cell and Professor Suda about other concepts of trying to reduce the cost of the reducing equivalents, whether it was improved ways to make sodium metal or whether it was actually ways to actually get around sodium metal and get to other reductants. And so, although there are a number of issues that still need to be worked, regeneration efficiency and developing pathways that allow you to at least get closer to the theoretical efficiency for BO to BH. And I would like to point out that if you look at the theoretical efficiency of going back BO to BH, you are within the DOE targets from an energy efficiency standpoint. Of course, right now there is no pathway that exists there. So fundamentally, it's not off the table, but from a pragmatic standpoint, we still need to increase the energy efficiency. Boron nitrogen compounds, the attempt is to avoid the formation of a stable BO bond. I think the most appealing aspect of these materials is the remarkably high amounts of hydrogen that are on these materials. We saw several hydrogen generation concepts in the posters and in the talks. Tom Autry talked about the mechanism of the thermal decomposition for this reaction in his talk, and I think people have seen his poster where they've looked at the effects of scaffolds to reduce the kinetic barriers for dehydrogenation. RTI has some concepts for how to do the thermal decomposition, and some other work, Los Alamos catalyst development, and Mark Bowden's poster talked about some substituent effects on thermodynamics and pathways. This one is where it looks like you can get the hydrogen off, but now the trick is going to be to put the hydrogen back on these spent materials, and so that really is where we are on BNHX regeneration. The last one, we saw a couple of really nice talks from Professor Saito and Alan Cooper on endothermic hydrogen generation from organic systems. Thermodynamics depends on the structure. Air products is very nicely shown. Heteroatom substitution can favorably alter those thermodynamics. There's been a lot of work, but probably a lot more work that needs to happen in catalyst development, both from a rate standpoint and from the ability to use non-precious metals on board a vehicle. So catalyst development is one of the key barriers there. So we didn't catalog all of the collaborations except to note that there were three that were in the sessions. Millennium Cell working with Icelandic New Energy, RTI working with the State Scientific Research Center in Moscow, and some discussions that Los Alamos and PNNL have been having with the Industrial Research Laboratory at New Zealand. I would not presume to tell you about any collaborations I don't know about, but I'm sure there are a number of others. Some of the areas that probably make sense for collaboration are, this is really a chemical process. It's about developing catalysts and catalytic processes to make these chemical processes go, whether that's rates, heat management, or the type of catalyst. The impurities and the impurity tolerance that the fuel cell can and will handle, and heat and materials balance with the fuel cell. Pretty interesting infrastructure questions in off-board regeneration in general, and what that might look like, and what some systems analysis might look like for that. One of the really appealing things to chemical hydrogen storage is these are fairly tractable materials. Most of them are molecular or oligomeric. They're very amenable to spectroscopic probes and mechanistic understanding, the way Tom showed us today for the ammonia-borane system. And this is an area that theory does a very good job on systems at this size right now, and can be useful for calculating thermodynamics and even for postulating some reaction intermediates. Onboard reactors, there's been some fairly simple concepts advanced, and we probably have some opportunity to develop some other concepts there. And as I said already, overall system engineering materials compatibility is going to be interesting and important in these reactive systems as well. And off-board regeneration, one of the themes that certainly came through is, if we're not going to just use hydrogen to put hydrogen back on for hydrogen storage, we probably need to come up with some less expensive reducing equivalents as we do our reduction, and build the reduction power back into the system that will then deliver hydrogen. So that was all I had. Thanks.
So now we'll step back, and Mark Steen from the European Commission will give us an overview and reminder of the objectives of IPHE and what the next steps are.
Thank you, Sunita. Okay. The International Partnership for the Hydrogen Economy, under which auspices this conference has been organized, has a mission statement. And I will read it carefully with you on this slide. To serve as a mechanism to organize and implement effective, efficient, and focused international research, development, demonstration, and commercial utilization activities which are related to hydrogen and fuel cell technologies. It's a mouthful, but there are a number of keywords in there. It is an organization which has as prime objective to serve as a mechanism to organize and implement. So it has a facilitating function. It is not a money pot. The International Partnership for the Hydrogen Economy has as signatures national member states, no organizations. That's also a point that you should consider. And any additional information you want to retrieve, you can easily find on the website, which is indicated on the bottom left corner. Oops. Now, the International Partnership for the Hydrogen Economy has two superimposed organizational bodies. One is a very high-level steering committee. Representatives from all the IFE members take the strategic decisions on the partnership. There is a second body, which is the working horse of the platform, if you wish, or of the partnership, which has a facilitating function explicitly, and it's called the Implementation and Liaison Committee. And the Implementation and Liaison Committee has been set up now more than 18 months ago, and it has as tasks to provide a forum for information exchange and discussing collaboration between the national representatives to IFE, from where recommendations can be forwarded to policy and decision makers of the IFE member states. This high-level function crystallizes or boils down into a number of more down-to-the-ground objectives of the Implementation and Liaison Committee, and in fact tasks of which it has been charged, namely to identify scope of research and demonstration activities which can benefit from IFE collaboration or other dimension. And this has already crystallized in the setting up of 5 so-called scoping papers. One related to hydrogen storage, one related to hydrogen production, one related to fuel cells, one related to regulations, codes, and standards, and the final one related to socio-economics. Now, these 5 scoping papers, who have been discussed and approved at Implementation and Liaison Committee level, who have also been endorsed by the steering committee, in fact set out the big picture, what the representatives from the national members of IPHE considered to be the research priorities. And again, these papers are public and you can consult them on the IPHE website. A second very tangible object or work of the Implementation and Liaison Committee is its function to acting as a catalyst for cooperation and for facilitating harmonization of activities by the members, which are related to topics which had been identified in the scoping papers and also in IPHE events, such as the conference that we are closing now. Now, the Implementation and Liaison Committee, therefore, has made sure that also in the scoping papers there are so-called targets and timelines which relate to very specific actions, and one of them is the first bullet there, organization of workshops and conferences. This is the first ever IPHE conference. There have been a number of smaller-sized, closed IPHE workshops already. Now, a second point that the Implementation and Liaison Committee in this context has been working on is to define what would qualify a joint collaboration exercise between member states from the IPHE as an IPHE project, and I'll come to that in just a moment. In order to guide the efforts in that area, the ILC has set up an internal project evaluation team, again calling upon the representatives from the member states, and that internal project evaluation team has a function to check the compliance of any joint collaboration proposal with the qualifiers which should be applicable to the project, but also to check on the content. So it's not just a formal check against administrative criteria. No, it isn't. And the last thing that the ILC should do is to feed evaluation results to the steering committee. The steering committee is the ultimate decision body in the IPHE. Now let me just remind and or clarify two major issues. IPHE projects necessarily have to rely on funding from within the IPHE member states. There is no new money pot just for IPHE projects. That does not exist. Which means that whenever a project or an event is proposed for IPHE dimension or IPHE labeling, then the individual initiators have to call upon funding mechanisms which are available in their own country. Maybe within their own country there can be an application for a dedicated funding towards opening an existing project or proposal towards the larger IPHE audience. This may be the case, this may not be the case. And obviously when embarking on trying to establishing a joint proposal, then because of the no money availability, it's clearly an incentive to explore in depth whatever existing agreements may already be there, bilateral, multilateral, or of any other nature. So that's the financing aspect. The second aspect is the topic that IPHE projects should be meeting or should be responding to. In fact, because of what I've been stating so far, the focus should really lie on pre-competitive collaborative research or development or demonstration. And the word pre-competitive here may mean different things in different contexts, but it's obviously an objective overall of the IPHE to disseminate information, to make information widely available among the members of the IPHE, be there from the industrialized world or be there from the developing world. So that makes it also more or less an implicit condition to deal with pre-competitive work. Now, if I summarize the conference, and I'm very grateful to the people who have been preceding in this presentation, I think it is worthwhile mentioning that the conference has achieved, in my opinion, definitely the objectives it had been originally aiming at. There has been a thorough overview of current state of the art and most recent technical progress, fine. There have been identified key barriers and areas for potential collaboration, and I refer to the presentations we have just seen now, and I'm sure that within the official part and also the evening parts, of the conference, there has been networking and explorational collaboration. So the audience to the conference, I think, has done its work. The scientific committee has done its work. Now it's up to the organizers of the conference to follow that up. And we, the four of us, we have to come up now with recommendations to the IPHE steering and implementation and liaison committee meeting on what is the outcome of this conference and what can be the follow-up of in activities. So what are these next steps? What do you have to do in order to be able to submit an IPHE proposal? First thing, check on the scoping paper. We are dealing here in the particular case with a hydrogen storage conference, the first ever for that matter, under the IPHE auspices, and I have to refer explicitly to that scoping paper, but also to the related ones. You will miss the word safety there. I can tell you that the word safety is included in the scoping paper on regulations, codes, and standards explicitly, and that safety aspects are touched upon in the other individual scoping papers. Now, having said so, and being reminded by Gary that maybe safety is the uppermost and most important issue, the second IPHE conference takes again place in this country, in Pisa in September, and is dedicated entirely to the safety issue. A second thing you would have to do if you are interested in preparing an IPHE proposal is to obviously continue technical discussion with your counterparts, and finally, if you decide to go ahead, and we would all encourage you to go ahead, is submit proposals through the website at the latest by September the 1st of 2005. Why this deadline? Because the steering committee is meeting in the second part of September 2005, and these are the people who have to finally endorse it. Now, to guide you in that process, you are free to submit draft proposals to the conference co-chairs. Please do so rather earlier than later because of the imminent holidays in different parts of the world. And then whenever we are confronted with the submission of a draft proposal, we'll try to informally feedback to you on the suggestions we may have. Now, what are the criteria that the evaluation committee will be definitely using, but which also you will have to consider in formulating your proposal, is there an IPHE dimension? So is there more than one IPHE partner working on the project, and is that working on the project also crystallized in some kind of an effective cooperation? Is it relevant for IPHE? In other words, does it comply with the recommendations set out in the scoping papers? Is there added value from the collaboration? And there are a number of criteria that you can consider in this respect. Does the proposal complement existing efforts without unnecessarily duplicating it? Does it allow to open up the scope of the work? Does it allow to progress in a faster way towards the end results? And is there any other added value? Now, in formulating a proposal, commitment will be looked for. And commitment can be exemplified by a clear formulation, for instance, of objectives, a strategic plan, and an annual work program. We don't want to formalize too much, but you have to give indications about these things. Are the partners' resources clearly identified? Remember, IPHE is not a money pot. And a final consideration is, because of the dissemination, which is one of the prime aims of the IPHE initiative at any rate, in how far is there reasonable assumptions that there will be an appropriate dissemination? So will the majority of the results be of non-proprietary nature? Are they clearly identified, etc.? Now, the template for proposal content can also be downloaded from the IPHE website. It contains a number of bullet points, and it's a maximum of 3 pages that we are looking for at this stage. Okay, I'll stop it there. In the particular area for hydrogen storage, Sunita will take over now. My main message is that there is scope for submitting proposals, yes. There is scope for working together, yes, and a number of examples have been identified already. There is some kind of a formalism that has to be followed, yes, but we'll try to minimize it as to the lowest possible level. Also, things are still under discussion at IPHE level as to the exact implementation. This is the first attempt to do such a thing. So maybe we'll make some mistakes, maybe we will have to adapt and modify some of the things that have been more or less tentatively agreed within the IPHE ILC so far. Bear with us, we'll try to do our best.
Thank you very much, Mark. I think that is exactly what people were looking for. And I'll finish by just summarizing some of the goals in the hydrogen storage area.
Excuse me, is it completely immoral to make a comment here? I'm talking. I am sometimes very slowly understanding reality, but there is one thing I don't understand at all, which is that all we heard now is perfectly all right if you have money in your office, but it does not make any sense to me if you have nothing to offer. So this repeated call for collaboration, I mean, is in fact useless in my view, because collaboration will occur anyway between people interested, and if you can only ask for collaboration if you have some money to invest. Now, I would be very happy to understand what you have in mind. I don't know any organization which is asking proposals, which is proposing an evaluation and so on, and has zero money in their office.
Okay, I take the comment. I also note the applause. The point that we have to deal with here is that IPHE is a top-down initiative, launched by the United States, endorsed as an initiative by a number of national governments. Realizing that, those people have just sketched, the government's representatives, have just sketched an overall plan that has to meet that mission objective, which I read very carefully. Now, the thing is that every individual project in an individual IPHE member state is thought to be able to benefit from opening up towards the IPHE audience. Yes. Opening up one way by, well, providing the output of their own results, but also benefiting from an inflow of other results. And it's clear those heads of government or representatives have not identified any money pot. That does not mean, as I've indicated, that in an individual IPHE signatory member state there may not be a reason to ask for additional money to open this up, to open an existing proposal, or to forward an existing proposal, or to step up an existing project to the IPHE dimension. And I know as a fact that the European Commission is considering that, and I know as a fact that a number of national representatives are considering that.
We heard from Gary Sandrock that there is almost every 2 weeks a conference on hydrogen. I mean, there will be several coming in this summer. I would say this conference was not especially cheap, and I would say if you have nothing to offer, rather than presenting the results and listening to the other people, every conference I know is doing that. So, I mean, again, I mean, what do you have to offer? What is more here than a standard conference yes. Everyone is attending?
I'll try to do my answer to your question. If tomorrow one project will have the label IPHE, in my opinion, such a project will have a priority inside each one country to have funds. That is the objective. You can say no, but that is our objective.
Yeah, just let me add to that, which I can corroborate. The second point is that you mentioned earlier, again, submitting a proposal subject to evaluation, etc., etc. Now, the evaluation is not an evaluation as you know it for applying for funding directly to your national or regional or even the Commission. It is much more streamlined. It is just checking on a number of criteria which I try to outline in the presentation, but in additionally it's not entirely limited to that, because the IPHE evaluation team, which is made up of members of the Implementation and Liaison Committee, or appointed by the Implementation and Liaison Committee, has to look at all those IPHE qualifiers. And I made explicitly reference to the dissemination. It's also technology transfer to the developing countries, which is involved in that. So there are a number of IPHE dimensional criteria which will be evaluated.
Maybe if I can also add to that, I agree that there are many exceptional conferences, and I don't think that the intent was to state that this was an unusually outstanding or different conference. I think we were attempting to match the technical standards of some of those other conferences. So I agree with Ron's statement, but I also think that it's important to say that IPHE is still very much in its infancy. It's still very much of a political entity, and our aim was to try to make sure that as it progresses as a technical asset as we look forward towards the hydrogen economy. So I think it's important to point to other examples of collaborations that don't have funding. So in that case, I disagree. But for instance, with the IEA Hydrogen Implementing Agreement, the IEA Annex 17 hydrogen storage activities have, I think, been an outstanding example of collaborations where the individual partners have their own funding. And that, I think, is what, as I go forward, I'll show you an example of what we'd proposed, which is really what Gary had presented as well. And I think the other point I'd like to make, and I do see a lot of the comments, and I think all of us agree to some extent and are attempting to, as we move IPHE forward, gather comments from the technical community to really improve the value added of IPHE. But to give you an example, if you start with high-level political support for IPHE, the idea is that the individual country members will provide that funding. No one country is going to be providing funding to all the countries to carry out research, but individual countries have already started the process of making funds available to both their own country as well as partners. And so, for example, I can just speak on with my own experience that we do have more support for providing funding for IPHE projects, and there are opportunities for other countries to submit proposals in cooperation with U.S. organizations. So that's just one example, and I know there are other examples as well with the EC where there could be additional funds available, but again, there's no one additional bureaucracy or additional set of proposals that you have to submit to another entity, the IPHE. But now I'd like to summarize since I know people still have to leave at 2:45, as Mark mentioned, there were scoping papers that were developed. They were approved by the steering committee and the ILC